last time, or I should start if there are any questions. Yeah.
What's the plan for the next week for you?
I meant to send out an email to make sure I got feedback from everyone. No. You didn't get an email about it, did you? No. Okay. So sorry. I'll figure that out. I mean, somehow if I don't come up with a better plan, I'll just do the classes on Zoom at the usual time. But maybe I'll look a little into. I'll continue contemplating that. All right. Any other questions? So we are talking about a week from today. There are 2 more weeks of classes. So I believe the last class is a week from Friday. All right, great. So last time we were talking about curves. And in particular, we were talking about how you could test whether curves are very ample, whether line bundles and curves are very ample, which of course is testing whether the curve is projective. So CB, a curve, and for simplicity, let's assume it's regular. And of course, by curve, I mean it's 1b integral separated and finite type. All right, and I had discussed a criterion for whether my curve is globally generated. So I want to phrase in a slightly different way. Sorry, whether my line bundle. So I'm given L a line bundle. And I can think about, on my line bundle L, there's a map to the skyscraper sheaf at any given point. So this is all going to be happening over a field, which for simplicity is going to be algebraically closed. So I can think of evaluation at a point P as a map of sheaves from L to the skyscraper sheaf. So, I never want to think about things as just maps between, sometimes I want to think about things as maps between spaces, but let me think about this in terms of sheaves. What's the kernel of this map? Well, it's the sections of L that vanish at P. So it's L tensored with O of minus P, whatever this means. Okay, and if I were going to get really fancy, I shouldn't have written the field itself here, right? So if my line bundle is trivial, then I can write O of minus P O and K sub P here. What this really is K tensored with the residue of LP. I can just write this as LP. So I look at the stalk of L at that point, and I mod out by the maximal ideal, which, because this is a regular curve, is principal. So I'm modding out by uniformizer. So the kind of picture to have in your head here of what's happening locally is, here I have T times OP CP. Here I have OCP. And here I have OCP mod times OCP. Okay. This is what's happening on the level of stalks. Right? These are both the stalks of line bundles, so they're free modules. This is a very much not free module. All right. So this is an exact sequence of sheaves. And one of the things we were cautioned about is when we take sections, that might not be exact. Right? So if I take sections, I can think about, here's my sections on C of L minus P. Here's my sections on C of L. So this map has to be injective, and its co-kernel has to inject into gamma C of the skyscraper sheaf, which is just this one-dimensional vector space. So this is isomorphic to the field K itself. This is one of the points where it's kind of helpful that I'm thinking about an algebraically closed field. If I weren't algebraically closed, I would have to worry about points where the residue field was a finite extension. But then I don't know whether this map is surjective. I mean, this is a one-dimensional vector space. So either this map is 0, and this map is an isomorphism, or this map is surjective, and this is the inclusion of a 1D subspace. So two possibilities. One is isomorphism, and then 0. The other one is inclusion of a proper subspace, and then this map is surjective. Okay. Theorem, if I always have 2, or I should say L is globally generated, i.e. base point free, if and only if 2 holds for all points. All right, and if you think this through, this is basically just a definition, right? 2 is exactly saying that there's a section of L which doesn't vanish at this point. And 1 exactly says, no, every function of L vanishes at this point. So this is an isomorphism. So there are generalizations of this, which maybe I won't get into proving. So what if instead of globally generated, this being base point free tells me I have a map? What if I wanted that map to be an embedding? I wanted it to be very ample. So L is very ample, which, as you'll recall, means that if I take the map that comes from all sections of L, then I get an embedding into projective space. If and only if, well, the equivalent of 2 holds, but with a slightly different map. So this is if for all P and Q, including the possibility that they are equal, I have that when I take the map sections on C of L minus P minus Q, sections of L to, well, now I have to look at the quotient. So sections of C of L mod L minus P minus Q. So if P and Q are different, that's going to be the skyscraper sheaves at 2 different points, right? And then what I'm checking here is can I get any possible pair of values at those 2 points? In particular, can I get a function that vanishes at one point and not the other, and vice versa? So exactly when I'll get very ampleness is when this sequence is always exact for all P and Q. What taking P and Q equal is measuring is the derivative of the map at that point 0, right? So distinct P and Q measures, do I get a bijection on closed points? And what the same P and Q measures, so P equals Q, measures is, am I getting an immersion? Am I getting something where the derivative is always injective? So you're measuring not only can I get a function with non-zero value there, I can get a function with non-zero value and non-zero derivative, and any pair of, or maybe a better way to say that would be a function with fixed value and with the value 0 and then a non-zero derivative. Okay. So let me not go through the proof of this, but that's kind of the picture to keep in your head, that if you want to check that something's is an isomorphism, you have to check that it's a bijection on points, and then you have to check that you didn't do something weird on the tangent space. Because there are these maps which are bijections on points, but not isomorphisms, like normalizing this cusp. So, right, if I took the map that sent my projective line onto this cusp, the problem I would have is here, I wouldn't get this surjectivity because the derivative goes to 0 at that point. Okay, great. Right, I'm talking about the map. T goes to T cubed, T squared. Cool. All right, so this seems like a pretty important question. When is this surjective? What property of L could I have that would guarantee this? Well, I'm trying to use this as motivation for why should we think about the general question of when this map on sections is exact, right? We sort of discussed this as a theoretical possibility at the start of the course, but we didn't have enough background to actually talk about interesting cases where it didn't work out. Whereas this shows you there definitely are interesting cases where it doesn't work out. For example, we saw in an elliptic curve, when I go from the structure sheaf to adding 1 point in my divisor, I always get option 1. I get the same space of sections. So at the point where I'm adding to the divisor, I have no non-vanishing functions. That's, of course, something that I sort of see as a problem. And on an elliptic curve, it turns out that's sort of the only issue. Once you start adding more past 1 point, then you're okay. But how do I know that? So what we're going to talk about today, among other things, is how do I know that? All right, well, we now kind of do have the background to talk about a lot of interesting examples of sequences where taking sections is not exact. So maybe the most important one to know is, so I look at P1. And of course, we know that there's a map from graded modules over KXY, C mod, to sheaves on P1. And the kind of key difference between projective things and affine things is, for affine schemes, I get an equivalence of categories by doing this. So I can only get an exact sequence afterwards if I started with an exact sequence of modules. But this functor, so it is exact, it sends exact sequences to exact sequences, but it also sends some non-trivial modules to zero. So things which weren't exact as sequences of modules in two variables become exact after applying this functor because I've killed their cohomology. And the kind of example to think about is here I have k of xy. Start this at the other end. So I'm going to have a three-term complex where I have every term is k of xy, but the maps between them are going to be in degree 1. So these guys have to have their grading shifted up by 1. These guys have to have their degree shifted up by 2 because I need homogeneous maps to get maps of sheaves. And these maps are, well, I send this copy of k of xy to x times this guy. I send this copy of k of xy to y times this guy. That has some kernel. What's the kernel? Well, it's things where I take a polynomial and I take minus x times that polynomial here and y times that polynomial. So right, I'm sending f comma g to xf plus yg. Right? And by the fact that polynomials are a UFD, the only way I can solve this equation is if g is divisible by x and f is divisible by y, and there's some h where I'm getting minus y h comma h. Oops, I should have stuck with the signs here. Okay, great. So this is a sequence of modules. It's a complex, but it's not exact on the right. Right? I have a non-trivial kernel, which is the field K itself. But what happens when I turn this into sheaves? This guy doesn't correspond to a non-trivial sheaf. Right? If I invert any positive degree thing, I will kill this module because every positive degree thing acts by 0. So when I turn this into sheaves, well, here I get O. Here I get O of minus 1 twice. And here I get O of minus 2. And this is exact on the right and the left. Okay, but if I take sections, that's just taking the degree 0 part of this complex, and that's not exact. Right? If I take sections, here I get 0, here I get 0, and here I get k. All right. So how do I think sort of systematically about when this is going to happen? I mean, of course, it's good to see examples like this, but it doesn't do you a lot of good if this just happens sometimes and you have no systematic way of thinking about it. So the systematic way of thinking about this is sheaf cohomology. So sheaf cohomology is a series of invariants of a sheaf. So let me sort of state this as a theorem where any sheaf of abelian groups on a topological space, there exist invariants hi of f, which are called the sheaf cohomology. I think many of you know at least a little bit about these. Some of you don't. I certainly can't assume that you do, but perhaps you have heard of these before. One really important thing to know is there are sort of many different ways of constructing these and thinking about them, and they're all equivalent. That's pretty important. So if in some other course you see some other way of thinking about these, and I'll try to at least gesture at a few different ones, they will end up all being the same. So the topological space part is pretty important. It depends on the underlying topological space structure. So there's sort of different ways of thinking about topological spaces. And the generalizations coming from a scheme. In this course, we're only going to be thinking about the usual underlying topological space. All right. So rather than try to write down an explicit definition of these, let me try to give you the important properties of them. So first important property, of course, is that H0, should really write this with the X in it. If I take H0, that's just the sections of. So sheaf cohomology is sort of a generalized set of sections. One way to think about this is sort of somehow, right, when you think about this case, what's happening here is somehow the number of sections aren't working out like you would expect, right? If I had an exact sequence, the number of sections here plus the number of sections here should be the number of sections here. That number isn't working out. In this case, the number of sections here equals the number of sections here, but there's another section here. And so this is telling us this guy should have some kind of like anti-section that's supposed to be canceling this guy. Well, sorry, should I have said supersection? There has to be some extra information that has something to do with sections, but which is kind of generalizing. And that's what sheaf cohomology does. All right, the other incredibly important generalization of this is if I have an exact sequence of sheaves, then there is a long exact sequence in homology. So it's easy to get mixed up about which way the maps go. The way to remember this is, well, you know which way the maps go on sections, right? So I should be, since these are some sort of generalization of sections, I should be getting hi of x goes to hi of g, goes to hi of h. And then it continues, but I increase the index. So when I have an exact sequence of sheaves, I don't necessarily get that hi of g surjects onto hi of h, but its failure to do so is measured by a map to hi of f. All right, so in some theoretical sense, this is all the information you need to define and compute sheaf cohomology groups. There's some helpful facts. You can learn about them, but the reason that sort of all the different ways of explicitly constructing them are the same is they all satisfy this property. And if you satisfy this property, and maybe one other obvious thing, you don't need anything else. All right, so in particular, now I sort of get some sense of what's supposed to be happening in these cases, right? I was trying to measure what happens once I go past this point. And now I know my long exact sequence tells me in this case, I should be considering 0 goes to H0 of C L minus P. So quite often people write H0 in place of gamma for sections, just to make sure there's extra information there. Oh, whoops. C L H0 B of the skyscraper sheaf, and then I go to H1 C of L minus P. So I see now the thing that causes me trouble is my L of minus P might have H1. And then, of course, that maps to H1 of C of L. That maps to H1 C of this skyscraper sheaf. And so, all right, are there any questions? Yeah. Yes. So one thing I could add in here as a property, H1 prime is HI of X F equals 0 for all negative I. Right? That's essentially left exactness. So in the parlance of homological algebra, this is a left-derived functor. There are also right-derived functors where the long exact sequence goes the other way. Right? Basically, with a right-derived functor, secretly what you're doing is now your indexing is by negative integers. And so instead of having I plus 1 here, you would have I minus 1.
I think so.
Well, I mean, this isn't enough in the, so I think maybe the one extra thing I would need to tell you, I'm not following Vakil's numbering here, is that if I take HI of F plus G, that's isomorphic to HI plus psi of C functorially. And maybe you still, I mean, the key thing I haven't said, because it's not how I want to think about things, right, is that if I have an injective object in the category of abelian groups in my topological space, which are kind of very strange beasts, but they do exist, their sheaf cohomology vanishes. And you should at least morally think that this is why. Maybe that's not technically implied by this, but right? This tells you that if you have a split exact sequence, then this is called the boundary map in your long exact sequence is always trivial, right? If I have a split exact sequence, then this sort of implies that this guy surjects onto here. So that's at least compatible with the idea that if you have an injective thing, all of these things will vanish. And once you fix that, then these are enough. But, for us, I don't think that's going to be the right way to think about things, because that's not usually what you use. Yeah. I think you need to do a little more work for that. Yeah. I mean, that's a kind of induction argument. So, right. I mean, so just as a example, right? There are lots of perfectly nice looking rings which don't have finite global dimension, where taking the right derived functor of hum of something into an object can have non-zero cohomology and arbitrary degree. It's genuinely subtle to figure out when an algebra has that property. So somehow you really have to use that topological spaces have some more structure than that. All right. All right, indeed. How do I compute this? All right, the usual trick for doing so is to resolve your sheaf. So I have my sheaf F, and a resolution of it just means I have an exact complex of sheaves, F0, 1, 2, etc. And the property I need, which of course I'm going to be making things feel kind of circular, is that if I take Fj, so this is for all j, and I positive, this cohomology vanishes. So this is kind of circular in the sense that, well, I have to be able to compute the cohomology of this guy. But there are lots of properties that sheaves can have that make their cohomology vanish. And in this case, you can apply the exact sequence to describe the cohomology of F in terms of the complex of sections of these things. So in this case, we have HI X F is equal to the kernel of the map from H0 of Fk to H0 of Fk plus 1 divided by the image of H0 of Fk minus 1 into of K. Right. So this is just the cohomology in the usual sense of the complex H0 of F0, H0 of F1, All right, and it's key, of course, that these higher guys vanish. So once you know that, you can relatively easily prove this by induction. All right, so no, I'm never, HK is always 0. So the point is how do I prove this? I prove this by using my long exact sequence, right? So for example, what's sort of the first step of the proof? The first step of the proof is I have a short exact sequence of sheaves, which is F maps to F0. What's the co-kernel of that? So this is an injective map. Well, the co-kernel is the image of F0 and F1, which is the same as the kernel of F1 mapping to F2. Right? So this is a short exact sequence, and I apply my long exact sequence to cohomology to it using the fact that all these higher guys vanish. I'm sorry. Yes, you're right. Okay. Mhm. I mean, this argument works when they're acyclic. Free is relevant for right exact functors because free things are projective. So what you would want is like co-free things, which the best version of that we have is injective. So one way to guarantee this holds is to take the FIs to be injective in the category of sheaves of abelian groups. Another kind of useful property, which there are a horrible number of multiplicities of names for things. So I hope I'm remembering this one right. I don't think I wrote it down in my notes. Another possibility is that this guy is what's called flask, which means that whenever I have the restriction map from FU to FV for V contained in U, this is always surjective. Yeah, no problem. Yeah, I mean, the key thing here is an injective sheaf is one where when it is the kernel of the short exact sequence, the short exact sequence always splits. Right? So for right-derived functors, you would be kind of worried about something bad happening with the quotient, right? If you think about like tensor product, it's quotients onto sort of bad things that make the tensor product fail to be injective at the left. Whereas if we're left-derived functors, the problem is with the kernel. Okay, cool. Yeah. Are these functors left adjunct? You mean the functor of this guy? You shouldn't think about the HIs as being sort of separate functors that would be adjunct to things. Sort of, it's really philosophically wrong to think of them as separate functors. You should think of them kind of all as one sort of object, which is a functor, but in some bigger, more complicated category. And then the adjoint is going to be the derived functor of the adjoint. I mean, that may be where this comes from, but I don't understand what all this, right? I mean, this comes from like the snake lemma, or, sort of, right? I think it's better to think about this is this is what you want to be true. And then sort of the snake lemma tells you that this is the right thing to do. So I'm not sure what you mean by all this. I think you're trying a little too hard to make something pure category theory when, like, right, if you're going to turn this all into pure category theory, the thing you should be doing is like saying, oh, we never should have thought about regular categories. We should have been thinking about DG categories the whole time. Which I'm not actually suggesting, but that's kind of the high level move here, is to think like, oh, I should never take cohomology. I should just think of the complex itself as the Hom space. All right. So let's talk about a few examples. This is a little bit off topic, but I think it's sort of important for philosophically understanding why all these things are the same. So for example, when I compute the singular cohomology of a topological space, apologize if you're not familiar with that. If so, just ignore the next minute or so. Right, when you read your algebraic topology book, they say I should take X and I should look at this complex of cochains on X. I'm going to C I plus 1, etc. But then actually, when you sort of learn the sheaf cohomology, you say, oh, I never should have thought about cochains of just the topological space. I should think about the sheaf Ci of X, which sends you to the group of singular cochains on U. And then when I have an open subset inside another open subset, I can restrict. This sheaf has this flask property. Whenever I have a singular cochain on V, I can always extend that to U. I could extend it to U by just taking 0 on everything in U, everything that wasn't in V. So the higher cohomology of this sheaf of cochains vanishes. So that tells me really what I was computing is the sheaf cohomology on X of the locally constant sheaf. Why the locally constant sheaf? Because that's the kernel of the map from C0 into C1. All right, so C0 is just functions on the set of points with absolutely no assumption of continuity or anything. But then C1 tells me, oh, what I have to do is being in the kernel of the map to C1 for, sort of reasonably path-connected space exactly means that I'm locally constant. So this is really what I'm computing, the sheaf cohomology of this constant sheaf. And that's, for example, why de Rham cohomology computes the same thing, because that's a different resolution of the same sheaf. Okay, but these are sheaves of abelian groups, but they're very much not coherent. So for coherent sheaves, we want a sort of different flavor of resolution, because there's some key properties of coherent sheaves that don't hold in general. So the other sort of thing, which, I mean, I could present this as an axiom, but it follows from the stuff we've already checked, just with a little bit of work. If X is an affine scheme, and here I'm thinking about the underlying Zariski topology on X, not actually using the affine scheme structure in any way. And F is quasi-coherent, of course, I'm using the affine scheme structure, and I say what it means to be a quasi-coherent sheaf. Then all the higher cohomology of F vanishes. Now, this is very much not true of other sheaves of revealing groups. Lots of affine varieties have lots of interesting singular cohomology. This is something special about quasi-coherent sheaves. It's something genuinely very different from, this is what would be called a constructible sheaf. All right, and I'm almost out of time. So the question becomes, how do we exploit this? Right? We know that in order to compute cohomology, what we want to do is resolve our sheaf in terms of sheaves whose cohomology vanishes. And if we're going to do that on a scheme, it seems what we need to do, or we would want to do, is to somehow take something that has some relation to affine scheme. So the way we're going to do this is let X be a scheme. UI and cover such that the intersection of an arbitrary subset of the UIs is affine. I'll just mention this is automatic if X is separated. If X is separated, then the intersection of two affine subvarieties is affine because it's the pre-image of an open affine in the product. And if I'm separated, then my diagonal map is affine because it's a closed embedding. So more generally, people will talk about the property of having affine diagonal, but in the kind of stuff we're thinking about, that usually just means separated. All right. So the way we can exploit this, and I'm out of time, so let me just kind of write it down quickly, is that we can resolve our sheaf using the restrictions to these affine subschemes. So I can take F, and then what I can do is I can map it to the sum over my indices of take the pullback of F by the inclusion of UI, and then take the push forward. So I'm going to call the inclusion of this guy into X, J sub I. So what is this guy? If you think about this in terms of the espacital, right? I have my sheaf, it's built out of a bunch of stalks over each point. I basically just take one of my open subsets and I throw out, I just kind of forget about all the stalks that aren't in UI. So I have to be a little bit careful because when I push forward, I actually get stalks back, but it's only kind of with information that's from the nearby stalks that are still in UI. All right, and then I map to pairs. Etc. All right, and these differentials always come from restriction. I have to throw in some signs. We'll talk about the details later. But when I take sections of this is what's called a check resolution. And because all of these UIs are affine, and all of their intersections are affine, these terms all have vanishing sheaf cohomology. And so they allow me to compute the sheaf cohomology of F. All right, that's all we have time for today. So we'll talk about this in more detail next time.